Welcome to another session of radio frequency IC design, and this is a lecture 6 unit 2. And from previous class we started discussing about system level architectures in RF. So in the previous class, just to recap, we started with by listing out the different receivers used. We are not looking at all the receivers. We will have look at traditional receivers and some modern receivers also, and transmitters. Then we started with the general consideration of the limited channel bandwidth that resulted in the complexity or the constraints that impose on the design of transceivers and receivers. Then we looked at the high Q factor requirement of filters when we use filters at the front end of receivers. Then we understood the difference between a band and a channel. With that, we also uh, we defined or we understood the basic heterodyne receiver. So in order to relax the requirements of the filter at the front end, the front end filter or the initial filter will in fact they will accept a band. That is why band selection is happened or at the front end of the receiver, and later by a process called heterodyning or mixing, the center frequency on which the data is there, that is your RF frequency, that RF frequency is shifted or it is down converted to a lower frequency, so that channel selection can be done somewhere down the line without much constraints on the filter. So that was the basic idea of a heterodyne receiver. And in the heterodyning process is usually happens like this. uh, 1 second. Yeah, so heterodyne process usually happens like this, and soon after heterodyning or soon after mixer, if you employ a low pass filter, you are in fact selecting the channel, because the center frequency is now shifted from omega in to omega in minus omega LO. That we have seen, and with that we just define the or we just saw the block diagram representation of a very basic heterodyne receiver, where there is a band select filter and a channel select filter. So band selection and channel selection which is happening at two points in the receiver, right? So to continue with this, we today we'll try to understand how this mixing or so this process we called here as heterodyning is in a receiver architecture we call that as down conversion mixing, right? So we'll just start with yeah, this is continuation in heterodyne receiver itself. So we'll start with down conversion mixing. So since down conversion is nothing but the translation of frequency from a higher value to a lower value. So down conversion mixing in heterodyne receivers. One more thing to keep in mind is the input coming at the mixer is soon after your low pass filter, sorry, a low noise amplifier, and before that you will have a band select filter. So the input to the mixer itself is a band, so always we should have that understanding. So since it is a band, that will have many channels. So we know that for a particular wireless standard, if a receiver is receiving a band, each band will have many number of channels depending on what wireless standard is that. So let me make that point here. Since the input to a mixer is a band, it will have contain many channels. So since a band is received or since a band is the input to the mixer, this down conversion can basically happen in two ways. So that way we call that there are two types of down conversion mixing. So the very first thing is say we have, this is our mixer and the two inputs to mixer, one is RF and another one is LO. So this frequency, a band is there, but in that band, say FRF1 is the FRF1 is the frequency there, and now that will be mixed using FLO. That will be mixed using FLO, and the output. So the output will be definitely some intermediate frequency. So it will be at FIF1. So this is the frequency, right? So what the two types what we generally do is we can either keep LO frequency as a constant one, so that for each RF frequency we will be down converting to each channel will be down converted into different IF channel, right? I don't know how you are getting. So let me just write that type here. So the first type we called as constant LO down conversion mixing, right? That means the input to the mixer is a band. It will be having different channels, so each channel will be mixed using the constant mixed using a constant LO frequency, and corresponding IF will be generated. Say the next band, the next channel, if it is at FRF2, that also will be given to the mixer, and that also will be mixed using the LO frequency located at the same LO located at the same frequency to get the IF. That will give you a different IF. So that will be FIF2, because FRF1 is mixed with one LO frequency to generate FIF1. Now FRF2 is different from FRF1. So if we use the same LO frequency, that will be down converted into a different IF frequency. So are you getting this? So what we do here is for a received N channel band, for a received N channel band, each channel in this band, each channel is down converted to a different IF channel. So each RF channel is down converted into a different IF channel such that LO frequency remains constant. So that is here LO remains constant. So just to represent it, we can write it as IF is varying with respect to FRF. So each RF channel is giving you a different IF channel, right? So this is one way to down convert, so that the LO frequency will be always stable or always constant. Now the other type can be instead of making LO frequency constant, what we can do is we can make this LO frequency variable. So what is the advantage if I keep this LO frequency variable? Any idea? If I change LO frequency with respect to RF frequency, yes, we can look for we can look for same IF for different RF. That is true, very true. So that is your second type. Yes.
Sir, in the second type, when we vary the LO frequency,
Yes.
we have to actually detect it at the receiver, right? So the architecture may become complex there.
Come again. You meant to vary this LO frequency is a problem you are telling?
So what I meant is when we vary this local oscillator frequency at the receiver, we have to detect which
Yes.
local
Yes.
oscillator frequency was used. So architecture may become complex there. So will it be
Yeah.
actually an advantage
I
with
didn't
respect?
hear. I didn't hear the last part, Vishnu.
Will it be an advantage with respect to receiver side also?
Yeah. We'll discuss that. Let me just complete this and we'll discuss that. Definitely, there are advantages and there are disadvantages. We'll discuss that. That's a good point, Vishnu. So constant. So the second one is constant IF down conversion mixing. So what happens here is uh, yeah, so it is clear that you will have one channel which is having some RF frequency that will be given to mixer, and for that we will have one LO frequency, say if it is FLO1, this will result in an IF frequency and I can call it as SFIF. Now similarly, if I look for another RF channel, say if it is FRF2, then I need to have an LO frequency so that your IF frequency will remain constant. So that will be FIF itself. So this is the second type of down conversion mixing. We call this as constant IF down conversion mixing. Yeah. So as Vishnu suggested, it seems like this is difficult to change the LO frequency every time with respect to RF and to generate an IF signal. But on the contrary, if you look at the previous case, see now we are especially if I look from the perspective of a heterodyne receiver, you have antenna. Soon after antenna, we have one filter which is a band pass filter. After that, there is an LNA, and then is your mixer coming. Now the channel selection is not yet done, only band selection is done. That is why we have all these channels down converted. Now channel selection has to happen here. Then after that you will have, if in certain cases there will be some more amplifier stages, then we have to do all the baseband processing, everything. But now the problem with this is each RF channel is giving you a different IF, so that the requirements down the receiver chain till the baseband is will be varying, because one, if it is FRF1, sorry, because the IF frequency is not at all constant, so that the first thing is you should have a variable filter itself soon after the mixer to select the channel at every time, and then all the baseband processing also has to happen at different IF frequencies, right? So in most of the cases, or generally, so in that way, the design or the design complexity is less when we have constant IF down conversion mixing. But at the same time, as Vishnu pointed out, detecting the signal, this FLO for each RF and down converting into a single IF itself is a task, and that is generally done with the help of something known as synthesizers or clock synthesizers. We call it as PLL. That will be we will be dealing about PLL in little detail in the last unit of RFIC, right? So just I can write one point here to simplify the design. So we are worried, or we are looking at the design part after the IF, after the mixing also, after the down conversion also, because if you are generating different IF frequency for each RF channel, then that will definitely make the design complex for the rest of the baseband and even for the filter also, right? So to simplify, the design of IF path, generally constant IF down conversion is used. Otherwise, what will happen? IF path will definitely need IF path requires a variable filter. Not a variable filter, a filter with variable center frequency.
So according
Yes.
to this, the first one, it has limited range of input that we frequencies that we can give if the filter is fixed at the output side, receiver side.
Come again?
According to this second statement,
Yes.
like if there is a maximum limit that the frequency can go up to, that means the input is limited. You cannot go beyond some certain range.
No, input is limited in the sense the input is a band, right?
Yes,
So
sir. So what
anyway we have a band select filter, so band will come in. Yes, yes.
beyond a certain frequency.
I missed Vishnu. What is that?
So you said that there we need a variable filter, but
Yes.
when we do it practically, filter will also have some limitations, like it cannot go beyond this frequency, no matter how much you
Yes.
vary.
Yes. Yes. Yes.
The
Yes.
input will be limited in that aspect.
Yes. Yes. True. Yes. That is true, Vishnu. Yeah. Right. So these are the two ways of down conversion. So one is constant LO and another one is constant IF. And for the reasons what I stated, this is generally preferred. But we will definitely see how a receiver will tune, or receiver will get to know what is the frequency and how they will always generate this constant IF. That also we will see probably in the last unit of our lecture, right? So this is about the types of down conversion mixing. Now let us quickly move to the next topic, where we'll try to understand what is called as this image problem, right? So let me just start with the heading. So problem of image in heterodyne receivers, right? This is a common problem when this heterodyne receivers were used for applications. So this problem is often called as image problem itself. So just to understand that, let me take the help of a spectrum, where I can mark actually the input signal and the LO frequency. Say we have an input signal here, and say this is the signal. This is a signal of interest, right, which is centered at omega in frequency. And now, yeah, so one more thing I just want to explain here. Let me, yeah, just do that first. Now for down conversion, in the down conversion mixer, we have to provide an LO frequency. Now the LO frequency can be given, or the LO frequency can be greater than omega in, or it can be lesser than omega in. So depending on that, we often use two terms to identify that. So that is, um, when this LO frequency is above the input frequency, we call it as high side injection. High side injection, it is called as HSI. And when the LO is below omega in, Karthik, can you mute? Yeah, when your LO frequency is below omega in, we call it as low side injection. So these are the technical terms what we use to identify whether your LO frequency is above omega in, or your LO frequency is below omega in. Right now, I am considering LO frequency, say which is somewhere here. Right. So by looking at the LO frequency, can you tell me what type of injection is this? Can I get a response in the chat box? Yeah, it is HSI. Sagar, I got it. I'm just waiting for everyone to respond, just to know how many are there. All right, Akash, Shashank. Neha, are you there? Neha?
Yes, sir.
All right, okay. Subramanya? Hello, Subramanya. Okay, yeah. So I'm getting, I think I'm getting responses more than 54 now. Okay, so this is HSI, which is high side injection, and your LO frequency is above or greater than omega in, right? So I am considering, so the input is, say I will write this as A cos omega in into t, even though I have shown it as a modulated signal. I'm just for the equation, just to mathematically modulate, I'm taking it as A cos omega in t, and this I'll consider as A cos omega in A cos omega into cos omega LO into t, right? So now if these are the two signals going to a mixer, I can definitely write that the intermediate frequency will be A cos omega if into t, and definitely there will be two components, but assuming that there is a high pass filter, I can say omega in minus omega LO into t, right? Or yeah, since it is cos, I can write either way. Now in this case it is omega LO minus omega in into t, because LO is the higher frequency. Now one thing what you can note from here is whether your omega in is greater than omega LO or your omega in is lesser than omega LO, the omega IF will be the same, right? So whether your omega in, so you can see that omega in is here on the left side of the omega LO. So whether it is here or if it is towards the right side also, both will have same effect only, or both will actually down convert into same frequency. So now, as I think Anirudh asked this question, so say this is omega in and this is omega LO, right? So the difference of these two, I can mark it as omega IF, because the difference frequency is omega IF. Now if I'm assuming I have an interferer which is omega IF frequency away on the right side of omega LO, and say this is that frequency, right? What will happen in the down? So if this is the input to a mixer, so now if this is going as the input to a mixer, this is going to mixer, and this is the LO frequency. So this is your cos omega LOT, and this is the input coming in, the signal of interest is coming in, but there is a component, you can consider that as an interferer or some other undecided signal at equidistant from omega LO towards the right side. So omega in is omega IF towards left side, but this signal, some undecided signal, is omega IF towards the right side. Now this is going to mixer, and after this, if I'm employing a low pass filter, whatever we do, if you look at the IF signal, so at the omega IF, I am expecting the desired signal. Desired signal will be there, it will be down converted and it will be there. Along with that, on the top of that, we will have this signal also. This undesired signal also will be down converted into same frequency, right? So this undesired signal frequency is often called as image, and we say this is image frequency, right? So the problem here is, so here the desired signal is at omega in, which is located below omega LO. At the same time, the interferer or the image signal is appearing above omega LO, and both this omega in, this is omega in and this is omega IM, are separated from the local oscillator frequency equally by plus omega f on one side and minus omega f on the other side. So therefore, now the desired signal is at omega. I can write the desired signal omega in is at omega LO minus omega IF, and the image frequency is at omega LO omega IF, right? So after mixing, both omega in and omega IM appears at the same frequency, and this will definitely corrupt the desired spectrum. So this is called as image problem. Now, therefore, since the problem of image can happen, we should be very careful how we choose the intermediate frequency, right? So, is there any doubt on this, on the problem of image? Can be removed by using, yes, yes, Divyanathan. Yeah, the idea is before mixer we can actually use a filter, yes. Now the question is, yeah, we are going to discuss that. We are going to discuss about the solution. Yeah, Divyanathan, if you want, you can unmute and speak. 1 second. The output is a superposition of both the signals, right? Nikhil, yeah, I'll come to you. Divyanathan.
Uh, Sir, in this case, we
Yeah,
know what is the omega n frequency and omega LO frequency.
yes.
So we can calculate the image frequency also from that and design a filter to remove these image frequencies.
Yes, that is true, and that can be done also. Now, when we calculate and when we try to employ that, so we are doing this before mixing, right?
Yes, sir.
Yeah. So when we do this before mixing, the previous problem why we are going for down conversion is still there.
Yeah.
Are you getting? Yeah. So what I meant is the frequency is still higher. That means the requirement on the filter is still bigger only. There is no relaxation on the filter requirements.
Yes, sir.
Yeah, but still we will use a filter, and that filter is called as image reject filter. But there is some trade-off. That is what we are going to discuss now. Yes, Devanathan. Thank you for pointing out that. Now,
Okay.
Nikhil, I didn't get. Yeah, Devanathan, is there something you want to tell?
Uh, no, sir, I'm done. Thank you.
Okay, okay, thank you. Nikhil, can you unmute and
Yes, sir. So when we pass the system through the mixer and low pass filter, the
mhm.
output that we get is the addition of two, isn't it?
It is low pass filter, right? So at the mixer output, you have two components, sum and difference component, and the sum component is eliminated by the low pass filter. That is what I have shown now in the screen.
Okay. Yes, sir.
You have doubt on that because here you will get omega in plus or minus omega LO, but here I'll get omega in only minus omega L, or the other way, omega LO minus omega. Yeah, I'll get only omega LO minus omega N because there is a low pass filter. Yes.
Yes, sir. Okay.
Because idea is in a receiver generally we prefer down conversion because we want to move from the higher frequency to lower frequency for the baseband operation. Is it clear, Nikhil?
Yes, sir.
Okay. Yes, Vishnu. So if LSI is used instead of HSI, will this problem still occur? Okay. So now, yes, Vishnu. Now, when you talk about LSI, it is similar, right? There also, the only thing is you will have signal on the right side, right? Your LO frequency will be smaller. Then also you can actually have image component towards the left. I hope you understand that. Okay. All right. When interferer is very close to omega in, Q factor requirement is high. Yes, yes, Nagaraj, that is true. Yes. Okay. So I hope you are with me. So let me continue and talk about what solution actually we can give for this image problem. Right. So as Divinathan suggested, what we do is generally we go for some filter. So to suppress images or image frequency, the common approach is actually to employ filters. Is to use filters where before mixer. Before mixer. and those filters we call as image reject filters also, since the intention of introducing that filter is to reject images, we call them as image reject filter. So now if you look at the so we are slowly developing a new architecture. So from the regular heterodyne receiver, we are slowly moving to a new architecture. That development is actually happening now. We have LNA, and soon after LNA is what we keep mixer, but now we understand that that will not work, or that will result in some images. So we are trying to include one more filter here before our mixer. So this is mixer, this is LNA, and this filter we call it as image reject filter. Now after this we have this mixing operation, and all those things has to be done, right? Now if I look at the output of this series of blocks including image reject filter, say I have a signal component somewhere at omega in, and the desired signal is at omega in, and say there is an image component somewhere here. Now if LO frequency, so image and signal both are equidistant from the LO frequency, that means the difference between the image and signal will be twice the intermediate frequency. I hope you follow that, right? So this will be 2 times omega if. This will be 2 times omega if. Now the whole idea is to introduce a image reject filter before this down conversion, so that we can eliminate the image, right? Now one question I'm asking, oh, there are so many discussions happening. If I use filter before mixer, then I should be operating at high frequency. Yes, Rakshak, that is true. We have to operate at high frequency only. That means the previous requirement, or the previous what to say, the constraint, not constraint, the previous the filter is still we have to work on the Q factor or the filter. Yeah, that constraint is still there. Yes, obtain a band of frequency. Okay, but the filter used in order to eliminate high frequency. Yes, yes, Anirudh. I don't know whether you are posing questions to me, but still I'm interfering and trying to give it some answer. So it is achievable. Yes, agreed. It would be a trade-off. Yes, Siddharth, it is definitely, it is a trade-off. Yeah. Now my question to you, those who are listening to me, the question is this: in order to do this image rejection filtering operation without burdening on the filter requirements, what can be done? We know that anyway a filter Q factor will be high. Now if filter Q factor is high, we know that practically achieving such sharp cutoff frequency filters are not possible. So what I can do maximum is I can just relax, or I can just relax the requirements of the filter, so I'll not get a sharp cutoff. So then if you want to eliminate image, what should be the solution at this stage? All right, Anirudh, why we would operating at high frequency? Just others, can you just stop posting comments, so I'll miss some of the comments. So Anirudh, your question is why am I operating at RF frequency? Is that your question?
No, sir. Like as Rakshak said, he said if I use the filter before the mixer, then I should be operating at high frequency. Sir, I didn't understand that point.
Oh, because see, the basic idea of this block, the block over here, what is the use of this block? This
For
mixer, yeah. So this mixer is in fact a frequency translator.
Yes, sir.
Right. So we are at RF frequency. We have a RF frequency signal that we are converting into IF frequency. That is what is happening in a super heterodyne receiver.
Yes, sir.
Right. Now, why am I doing this? because ultimately I want to process channel information. Yeah, channel information, and only if I down convert, or only if I translate to a lower frequency, I can easily filter out the components, right?
Yes, sir.
The filter, the relaxation on the filter is a little bit more. Probably Rakshak was meant about this frequency as high, because still it is omega RF. We did not do any conversion before mixer.
Yeah, yes, sir. We
Okay.
are at a higher frequency, so I have to design a filter which is of higher frequency, and that will cost more.
Yeah, the same
Okay.
constraint is still existing, since I am trying to introduce a filter before mixer.
Oh, yes, sir. Got it, sir. I had a different reference. Yes, sir. Got it.
All right. Okay. Yeah. So thank you for
Sir,
yes.
what if we did this in stages?
I didn't get
Before
Vishnu.
the amplifier? What if we did this in stages? Like we used more than one local oscillator. Slowly,
Yeah.
slowly we bring.
Yeah, I hope, yeah, all of you are actually coming to the solutions what I am going to discuss. That is good that you are getting the solutions even before discussing. Yes.
Also.
Yes, Vishnu.
Sir, in this, I had a question regarding this. If
Yes.
we're doing LSI, then we need to reject the image on one side of the
Yes.
local oscillator frequency, and if we're doing
Hmm.
LSI on the other side,
Yes.
how would the image reject filter know which side it is?
So that depends on the frequency, right? When you say left or right, again there is a band, and we are actually designing a filter with a center frequency with a band of interest. So whether it is on whether we are doing LSI or HSI, the difference between the omega in and omega the input frequency and the image frequency is twice of omega IF itself, right?
Yes, sir.
Yeah. So depending on that only we will process further. So let me just finish this. I don't think we can reach to the next architecture, but still I'll try to complete. Yeah. So all of you are coming to the solution itself. So I am just reading out the other. Siddharth, it is a trade-off. As yes, they increase the value of 2 omega IF is one solution. Make the difference to omega high. Yes, Nikhil. Yes, that is right. Omega L very close to omega n in the first stage. Omega n minus omega L would be very close to omega n, so the interferer would be far away. Then we could filter out that part. I didn't exactly get that, Nagaraj. I'll come back and discuss. Let me just finish this. So my question here is, if I want to have a reject filter before mixer, and this reject filter has to reject the image. Now to make the give some relaxation on the filter requirement. So say what I want to do here is I want to take out only this omega in. So I'm looking for a image for a filter which is having this kind of response. Right. Now, if I want to relax the requirements on this filter, what I can do is I can keep this 2 omega IF very high. So, or if your omega IF is very high, the requirements are we can relax the requirements on this image reject filter. Right, because if your omega IF is high, your image will appear very at a larger distance only, or it will be far away from your signal of interest, and easily with a filter, even though the filter is centered at a high frequency, we don't need to worry much about the selectivity part, because there are a lot of relaxation. So we can have a not a very sharp cutoff, but still with a relaxed filter we can remove the image, and we can take out the signal itself. But the problem there is, so the point here is to maximize. So here we are trying to actually reject image. So to maximize image rejection, if we want to maximize this image rejection, what I can do is I can go for large omega IF, right? So that result in 2 omega if will be still larger, so that that will be definitely out of band, or it can be eliminated. But the problem is there is a limitation to this maximum value of 2 omega if, right? Because I cannot increase this omega if like anything, because the whole idea of converting from RF frequency to IF is just to have relaxation on the, or just to make the center frequency to the lower side and have a better filter, and to select the channel and further process it, right? So if I am trying to do image rejection with a relaxed filter, and for that if I am keeping omega f very high, then that is another hit, right? The point here is, when I try to do a better image rejection, there will be constraint on the channel selection which is coming after this, because now I have omega if here. Now I told that channel selection cannot be done at the beginning, because since the bandwidth is very small, the Q requirement and the filter will have much complexity. Now that is why we are doing this mixing operation and keeping omega f low. Now if I want to do for image rejection, if I still want to keep omega if high, then the channel selection is at stake, right? So that means we are coming to a point that there is a trade-off between this image rejection and channel selection, right? So to better reject to make image rejection high, if you try to keep large omega if, then channel selection will be difficult, and the other way, right? So there is a trade-off exists between these two. Yes, Nagaraj. Yeah. So our requirement is to make omega if low, but if I am introducing an image reject filter, then to do better image rejection, I should keep omega if high. So that is that is actually a contradiction. That is why I told there is a trade-off between these two. Omega if is omega in minus omega. Yes, there is a trade-off. Yes, Nagaraj. Very true. Right. So in heterodyne receivers, in order to make channel selection easy, we down convert the RF input frequency to an IF value. That is done by this down conversion, so that at a low IF, we can actually design a better channel select filter. Now the trade-off is there between this image rejection and channel selection. So let me just code that here. So to reject, this is very important point to understand. So to reject image frequency, to reject omega im, if omega if is kept large, then this will affect the channel select filter Q. Q of the channel selector filter will be high to practically achieve it. Right, this is one thing. And the second thing is, now if we keep omega if low, then we can do channel selection better. Then the channel selection filters Q can be made reasonable, but the image problem will be severe, right? So let me yeah, so that is what you can see here. So if you look at this this diagram, you can see that see, in the first stage, I am trying to keep a very large omega if. So you can see that omega if is kept large, so that so I am actually able to reject the images. Images can be reject, and this is the image selector, image reject filter carrier, and it can easily take out the desired channel, and it can reject the images. But because of this large omega IF, I cannot be able to design a better channel select filter so that even the close interferers cannot be removed properly, because now there is constraints, or there is much constraints on the cutoff frequency or the characteristics of this filter because of this large omega IF. I cannot get a filter with a proper Q, and so that the close by interferers will be still there. So when that will be down converted, definitely that will corrupt the signal to some extent. Now on the other side, if I'm trying to keep omega if very low, you can see that here your omega IF is very low. Now if I do that, what happens is, since omega IF is low, I can design a better channel select filter that can in fact reject the very close by interferers, but your image problem will be still there. So this will be so image problem will be, you can see that here it will be large compared to here. Here it will be very small, right? So this is the trade-off between the image rejection and channel selection. So you can see that this is your image reject filter response in the two cases, and this is the channel select filter and the response in the two cases, right? So this trade-off exists. With this trade-off only, actually we are moving to the next architecture that we will see in the next class, right? So what we discussed today is, we discussed about the types of down conversion mixing in heterodyne receivers, and we stated that to simplify the design of the IF path, we generally go for constant IF down conversion mixing, and then we understood what is the problem of image and how it can be solved by using an image reject filter, and what is the trade-off then between the image rejection and channel selection, right? So now we will move to the next architecture with this understanding that will continue in next class. Thank you so much for joining today's class.